Welcome to ETE MCQs. Now let us solve a problem in digital circuit. The question is, the truth table of a circuit is shown below. So you have got three inputs, A, B and C. All the three are inputs. A, B and C. All the three are inputs. Y is your output. Obviously you have 8 possible combinations. The respective output is given for us and we are supposed to find the Boolean expression for Y. The Boolean expression of Y has to be identified. So in order to find, you can just notice the Boolean expression is nothing but Boolean addition of three products. If it is Boolean addition of three products, then it is fine to go ahead with K-map. We have three variables. Once you have three variables, then we should have a K-map with 8 cells. So to find the Boolean expression, let us go for K-map. We need to have a K-map with 8 cells. So let us take it as A, B and C. 0, 1, 0, 0, 0, 1, 1, 1 and 1, 0. Okay, this is what we have. So you can just notice the minterm that corresponds to 0, 1, 1 is 1. The minterm that corresponds to 0, 1, 1. 0, 1, 1 is 1. Next, for 1, 0, 1 it is again 1. For 1, 1, 0 it is 1. For 1, 1, 1 it is again 1. For 1, 1, 1 it is 1. In order to find the minimized Boolean expression, when you would like to perform the grouping, look for the one which has got only one possible way to group. I can just notice this one can be grouped, that is the one which is in the element, which is in the cell 110 can be grouped only with its neighboring one. That is the only possible combination. So this can be taken as the first grouping. So this grouping is fine. Okay, so this grouping is fine. So Y is nothing but the product term that corresponds to this grouping is, it is A, because A is 1 throughout this row. So A is 1 and B changes from, B remains 1 here, whereas C is 1 here and here it becomes 0. So the product term is going to be AB because B is 1. And the next grouping we can consider this particular one. This one is can be grouped, that is the one which corresponds to the cell 101 can be grouped only with its neighboring one. So this grouping is far preferred. So go ahead with this grouping so that this one is grouped. The first grouping was performed in order to cover this particular one, cover this element. The second grouping is performed in order to cover the element 101. Okay, so plus the respective term is A is constant throughout, so take it as A, whereas B changes from 0 to 1, so you won't be having a B for this grouping, whereas C is constant in both the cells, so it is AC. The second term is AC. Likewise, the only one that is left out is the one which corresponds to the cell 0, 1, 1. So if we perform the grouping, we can notice that the only possible combination that we can group is this grouping is fine. So when you perform this grouping, what you get is B and C is constant. In this column you can notice B and C is constant throughout, it is 1, whereas A changes from 0 to 1, so it is plus B, C. So if you notice the final resulting Boolean expression we get is nothing but Y is equal to AB plus AC plus BC. So among the options, B is correct. AB plus AC plus BC. You can notice now all the three implicants are or essential prime implicants. All the three are essential prime implicants. All the three are essential prime implicants. The reason is the first grouping is basically performed, the only that particular grouping includes the 1 that corresponds to 110, and in the second case, for the sake of the 1 in the cell 101, the grouping is performed. No other implicant will or prime implicant will help you to do this grouping. Likewise, the third grouping or the third product term is contributed or basically happened due to this 011 cell, the 1 in the 011 cell. For the sake of this one, this grouping is performed. So all the three corresponds to an essential prime implicant. Now we are supposed to find an alternative expression, Boolean expression for y. This is based on K-map. There can be more than one Boolean expression that corresponds to a function. Function y can have more than one Boolean expression. Okay, there is no restriction on this. It can have more than one Boolean expression. Now that we have obtained the Boolean expression using K-map, we can also obtain the Boolean expression using based on Boolean expression minimization method. By applying laws, you can minimize it. What you do is, we are supposed to get the function y, and we are supposed to obtain a Boolean expression that produces a 1, okay, for y. So there are just 4 possible cases that we are supposed to consider. We don't have to bother about the zeros, okay, because the function or the Boolean expression shouldn't have to produce any output for these cases. We need to consider only ones. The output 1 and its respective minterm has to be taken. Okay, if I consider the first one, the respective minterm is a bar bc. I am just considering this one as the first term. So I will have a bar bc. Next I am considering the second minterm. It is a b bar c, Boolean or with a b bar c, Boolean and with, sorry, a Boolean and with b bar c. Again Boolean or with ABC bar. Next it is, here it is, I am considering this term, so I have AB C bar, A B C bar, Boolean or with, finally it is ABC, A B C. Now let us just try to rearrange and reorganize it. Once you do that, we will end up with, you can just notice, I can just rewrite the first two terms. Among the first two terms, I can just take it as A bar B based on distributive law plus A B bar dot Boolean and with C, plus the next case I am taking AB common, so that I get C plus C bar, and we know that C plus C bar is 1 in all the cases. This is going to be 1. So finally I can just obtain, and we know that the Boolean function of A XOR B is nothing but A bar B plus A B bar, A bar B plus A B bar. So based on that, I can rewrite it as A XOR B dot C plus AB. So now let us draw the circuit diagram of the finally obtained Boolean expression for y. The circuit diagram can be of this form: A, B, and C. So initially we have A XOR B, A XOR B. This part is A XOR B. It has to be taken dot product with C. So it should be taken dot product with, that is Boolean and with C, and this is your, you again have AB. So you take A and B, both of which to be are supposed to be Boolean ANDed, and it is given as input to AND gate. It is taken outside. So this should be given as input to a OR gate. So the resulting expression, the interconnect becomes Y. So this is the respective circuit diagram. Likewise, we can draw a simple circuit diagram for the Boolean expression that is obtained using Okay, ma'am. I'm just doing it for your understanding purpose. What I mean to say is the same function y can be implemented using k, ma'am. You get an expression. And when it is implemented using Boolean laws, realized using Boolean laws, you get some other expression. But both of which are mathematically or in terms of Boolean algebra, both of which are equal and they are valid. Okay. And then we have A, B, and C. Here A and B are given as input to AND gate. Next, B and C has to be taken. So I am just taking it along with B and C. You get the other term, and then you have A and C. So for A and C, all the three are given as input to the OR gate, three input OR gate, and this is your output. So what I mean to say is one function can have multiple Boolean representation or Boolean expressions, and it can have, obviously, once it has more than one Boolean expression, it can have more than one way to realize its respective digital circuit using logic gates. But both of which are mathematically, both of which are equivalent. They are one and the same. It implements the same functionality. Both the circuits will produce the output Y comfortably. Okay. Thank you.